All right, ladies and gentlemen, we'll get you guys going this week. So basically, yesterday I had you guys do uh, Newton's quotient, which is really a rule. This is the idea of Newton's quotient right here. It's literally the limit definition. So what we're really looking for, as I asked you, you look to see what contains in H. So if we're looking at this and we take a 2 out, that's the way I look at it, because we're really finding f of 2 right here because it's 2 squared. If we take that out, we get x plus h squared minus x squared over h. So my function really is x squared because I'm plugging in 2 and squaring it. Okay. The key spot really to look is right here because that's what we're looking for, just like that. So you look here and then you match it up to what's going on here. So that's the idea of kind of dealing with these functions. So if you look at this right here, we have an plus h right here. So we know that this is going to be our x plus h, and this is going to be minus f of x. And so now I've just got to figure out what function it is. So if I have an 8 here, how do I go from here to here? Well, they took the cube root, so then that means that my function is the cube root of x, and then you can just take the derivative of x to the 1/3, and then you find it from there. So that's really all yesterday's was, plus some review. So we're really working on that limit definition of slope. Remember, we keep talking about that. It's always something to do with slope over the change in x. And so we want that change in x to be 0. So that was yesterday's deal. Today's going to be a little bit different. So like right now, let's say I give you this graph and let's just do the square root of x. Okay, so then this function is f of x equals the square root of x. And then if I wanted you to find the area under the curve, we would go from here to here, right? And we take the integral of a to b, and that would be of, go backwards here, the square root of x. And you guys would find the integral, and then we'd find the area under the curve, okay? So we have this idea, though, that that's two-dimensional, but we live in a three-dimensional world, and so if it's three-dimensional, how do we make something like this three-dimensional? And it's pretty much called like rotational volumes, and you spin this thing around the axis, so we can have an x-axis here, and we can have a y-axis here. And it creates different shapes if you kind of look at it here. So this is where you think I can't draw straight lines up and down. Wait till you see me try to draw a circle on this thing. So the idea is if I take this and I rotate it around the x-axis, I get a circle out of it. So if I rotate it around the x-axis like this, see, I told you that circle, I get this circle out of it. Okay, it's not very good three-dimensional, but I'll show you a better model here. It's hard to draw three-dimensional. And another way to look at it is if I take this here and I have this piece like this. Sorry, my alarm's going off. And I rotate this around the x-axis, let's say, it'll rotate and I'll get the bottom of it, right? So it'll rotate around and I get 2 of them. Well, if I cut this thing like this, I cut this and it's been rotated around the x-axis, I'm looking at a circle like this. So if I cut it and I look at it from this side, let's say, it's really hard to visualize, guys. I usually have like little things in the classroom we can look at it. I have this idea that I've got a disk, and this center circle right there, that's the x-axis. The x-axis is the center, and the function, or this on the outside, is f of x. So the outside line, outside, is f of x. I know that's really kind of hard to see, and we'll have a little bit better idea. So if we rotate something around the x-axis, it creates the circle. So really what we're looking at is the area of a circle. So if we're looking at the area of a circle, all I need to figure out is what's the radius here. So the radius is going to, so we need to figure out how do I find the radius of that rotation piece. And that'll be the key point for you guys right now, is how do I find the radius. So the radius really is going to be the outer minus the inner. Kind of like upper minus the lower. You can even draw it this way if you want. It's going to be upper minus the lower. However you want to look at it here. So if we're doing outer minus inner, it's going to be f of x minus the x-axis. Well, the x-axis is going to be 0 right now, so we really have f of x minus 0. So we know the radius of this circle is going to be f of x right now, because we're just sitting on the x-axis all the time. All right, so that's the basic idea. I know I may have not, because you can't visualize it. It's super, super hard. I get it. So what do we need to find the volumes of rotations? Number one, is it on the x-axis or the y-axis? That is crucial, and I'll show you here in a second. Or the y-axis. And then we also have to find the radius. Oops, radius. That's what we need. So on the x-axis, let's just take that one we were looking at here. If we're rotating this way on the x-axis, it's going to rotate around like this. I think that was the best one I've ever done right there. And we've got a circle right here where we've got to find the radius of this. And it's just going to be from the x-axis up to the function. So our radius is going to be r equals the square root of x, because that's what this function is. It's the square root of x. That's for the x-axis, so it's really crucial we find out where we're rotating so we can draw this. Now if I change this and I still use the same function, but I rotate around the y-axis, that means when it rotates around, it's going to create a shape that looks like this, and I have this idea that I've got a flat top to it. It almost makes it look like a cup or kind of idea, if you guys can kind of visualize that. I know my drawings are absolutely amazing. So we've got this idea that I've got a circle that is, you can look at it from the top. So if we do that, we know that that circle if we cut it along the y-axis, that circle is going to be an outer minus an inner, or the outside minus the inside. Well, this outside circle, if we're looking at it, is a y because we're going from here to here. So we've got to kind of look at this differently. If this is the square root of x equals y, then I've got to rewrite this. I can't use the square root of x because I'm not on the x-axis. I'm on the y-axis. I have to do it in terms of y. So that means x equals y squared. So in terms of y, the radius will be y squared minus 0. And so my radius is equal to y squared. So right now, if we're solving on the x-axis, we're solving for y and writing it in terms of x. And if we're solving for the y-axis, if we're working with the y-axis, we're solving for x and writing it in terms of y. Changes everything. Okay, guys? Unfortunately, it changes everything. So here we go. So here's what you got. We call this the DISK method because we're really, when we do a cross-section like this, we actually create a disk, okay, with a center to it. So basically we were creating a circle. So we know that that area is pi r squared, right? We're dealing with pi r squared. Now, since it's pi r squared and this is a constant, we just move the pi out front, and we're doing r squared for the area. I mean for the radius. Okay, so that's the formula you need for today. All we have to do, if you notice, is figure out what r is, and then we can integrate it from there. So, told you there's much better drawings. So, our original piece is y equals x squared. So our original piece is y equals x squared. And when we rotate this thing around the y-axis, this is the key piece, when we rotate it around the y-axis, we create a disk that is right here. And we've got to find the radius from here to here. That's the key piece. Doesn't matter where it's at, because when we're taking the integral, we're taking a bunch of small little circles and washers stacked on each other, right? So we're still dealing with integration, because integration is still, this is like three-dimensional Riemann sums where we're adding the area of a circle now. So if we cut this out, we've got this big flat disk that's got a little height to it, and this one, the radius gets a little bit bigger, and we keep rolling through these things one more at a time. So it's the sum of all these circles that are cut in half. And you can kind of see a better visual here. There's one here, one there, one there, one there, one there, and it just keeps kind of getting bigger and bigger until you get to the final top piece. So we've got this piece here. It's the volume of y equals x squared, which we know. So y equals x squared is our function. And the boundary is y equals 4. So this top part here is y equals 4. So since we're on the y-axis, we need to solve for x. So what we do here is, since it's on the y-axis, we solve for x. And if we solve for x, we take the square root of x squared, and so we end up with x equals the square root of y. So we solved for x. Now we have the radius in terms of y. So we've got the square root of y, so r is equal to the square root of y. And then we know now that r, I'm gonna do this down here a little bit closer so you guys can see it. So I'm gonna take all this stuff and I'm gonna write it right here. We know that the volume of this thing is equal to pi times the integral from 0 to 4, because the 4 is the top boundary. Here's my lower boundary. Here's my upper boundary. 0 to 4 of my radius. It's got to be in terms of y, square root of y. I have to square that. Don't forget, it's pi r squared dy. And then I just clean this up. V equals pi 0 to 4 of y dy. So squaring a square root just gives me y. And then from there, I integrate it. So they integrated it, add 1 and divide. That's where they get y squared over 2. And then we just plug it in. 4 gets plugged in, and 0 gets you nothing, so you end up with 8 pi. So we're really just working with integrals, everyone. And I know it looks a little bit crazier, but we're just working with integrals, and we just have to find our piece where it's a to b. Right now we're using pi r squared. You just need to find r in either terms of y if we're working with the y-axis, or terms of x if we're working with the x-axis. So what does this thing look like on the x-axis? So let's just take it here. Y equals x squared, and we're going to rotate on the x. Okay? So we're going to take that same graph, and here's our y equals x squared. And I'm going to go ahead and stop it at 4, and it's going to go to x equals 4. So at 4, I stop it. So I know my a is going to be 0, and my b is going to be 4. Because I'm going to rotate it on the x, so that means it rotates this way. And I get a shape that looks like that with my circle over here. I know that's horrible. Quit laughing at my circles. That is horrible. So I've got circles cut this way, and then I cut another one, and another one, and another one, and another one, and they just get bigger and bigger and bigger as I go. So every time I slice this, I get a circle. And the circle has a radius from the center to the outside, and that radius is x squared. Because I'm on the x-axis, I solve for y, and I'm in terms of x squared. So I've got a is 0, b is 4, the radius is the function on the outside, which is x squared. So then I know that the volume is equal to pi, and from 0 to 4 of x squared dx. So then I can integrate this thing. dv, I'm just going to say, I don't want to do dv, don't worry about that right now. So we're going to do this, which is equal to pi times x to the 5th over 5 from evaluated from 4 to 0. So then I know 0 is going to give me nothing, so I get pi times 4 to the 5th power divided by 5, and that gives me some ugly fraction of 4 to the 4th, 256? No. 4 to the 3rd is 256. What's 4 times 256? 1,024 over 5. I believe it's right. Someone check the calculator for me on that one. 1,024 over pi. So I know this is a little overwhelming on a video, but remember, we're just finding our radius, plug it in to do the algebra, and then evaluating it at our boundaries right now. So they've got to tell you the boundaries. You got to find a and b. You got to find the radius, and that radius, and I'm going to reiterate that piece right there. Okay? X-axis, the radius, solve for y, and then use X. And if it's the y-axis, solve for X and use Y. That's the key piece right there. Okay, so I'll post it, worksheet 49. Good luck on that, guys. We've got some time this week to kind of clean it up, but doing the best we can, keeping you guys moving forward. Good luck, and let's rock and roll. I don't know why it did that, but we'll just figure out how to get off of this. I'll just do that, and we'll end. We'll see you guys later.